Hello, everyone. Welcome back to another exciting physics session. Let's kick things off with a question. How do you measure the heat absorbed by a substance when it changes temperature? The answer is calorimetry, a method used to measure heat transfer during thermal processes. In a calorimetry experiment, a device called a calorimeter is used to measure the heat gained or lost by a substance. The basic principle is simple. The heat lost by a hot object equals the heat gained by a cold object. It's just the law of conservation of energy at work. Now, let's explore the law of mixtures. This law states that when two objects of different temperatures are mixed, the heat lost by the hot substance will always equal the heat gained by the cold substance. We can express this mathematically as mass sub 1 times specific heat sub 1 times open bracket temperature sub 1 minus final temperature close bracket equals mass sub 2 times specific heat sub 2 times open bracket final temperature minus temperature sub 2 close bracket. To make this clear, here's what each term means. A mass sub 1 and mass sub 2 are the masses of the hot and cold objects, measured in kilograms. Specific heat sub 1 and specific heat sub 2 are their specific heat capacities, measured in joules per kilogram per Kelvin. Temperature sub 1 and temperature sub 2 are their initial temperatures in degrees Celsius or kelvins. Final temperature is the final equilibrium temperature of both objects. Using this equation, we can determine the specific heat of a material by mixing it with another known substance and measuring the final temperature. That's the beauty of the law of mixtures. It allows us to find unknown quantities by measuring the temperature change. Next up, let's talk about the devices we use to measure heat, calorimeters. There are two main types of calorimeters: the constant pressure calorimeter, which is open to the atmosphere and measures heat at constant pressure. The constant volume calorimeter, also called a bomb calorimeter, which is used for reactions where the volume doesn't change, like combustion reactions. The key to accurate calorimetry is insulation. Calorimeters are designed to minimize heat loss to the environment, ensuring that all heat measured is only the heat exchanged between the substances inside. Here's a quick equation for heat exchange. Heat equals mass sub 1 times specific heat sub 1 times open bracket temperature sub 1 minus final temperature close bracket plus the water equivalent of calorimeter times open bracket final temperature minus temperature sub 2 close bracket. The water equivalent of the calorimeter is a correction factor that accounts for the heat absorbed by the calorimeter itself. As shown in the diagram, calorimeters help us isolate heat flow and ensure we get precise measurements during experiments. Now, let's take a deeper dive into the heat capacity of the calorimeter. Heat capacity is the amount of heat needed to raise the temperature of the calorimeter by 1 Kelvin. But we also have the water equivalent, which represents the calorimeter's heat capacity. The water equivalent tells us how much water would need to absorb the same amount of heat as the calorimeter for the same temperature change. The total heat exchanged is then heat equals mass sub 1 times specific heat sub 1 times open bracket temperature sub 1 minus final temperature close bracket plus the water equivalent of calorimeter times open bracket final temperature minus temperature sub 2 close bracket. This equation helps us correct for the calorimeter's heat absorption, ensuring our final measurement is accurate. In the diagram, you'll see how a calorimeter's water equivalent is accounted for in the calculations, giving us the precise heat exchange. Now, let's work through a practical example. We have a copper block with a mass sub 1 equals 0.5 kilograms, heated to a temperature sub 1 equals 100 degrees Celsius. This block is dropped into a calorimeter containing 1.0 kilograms of water, initially at temperature sub 2 equals 20 degrees Celsius. The final temperature is 50 degrees Celsius. we need to find the specific heat of copper. Using the law of mixtures equation, mass sub 1 times specific heat sub 1 times open bracket temperature sub 1 minus final temperature close bracket equals mass sub 2 times specific heat sub 2 times open bracket final temperature minus temperature sub 2 close bracket. We substitute the given values. 0.5 times specific heat sub 1 times open bracket 100 minus 50 close bracket equals 1.0 times 4186 times open bracket 50 minus 20 close bracket. Simplifying, 0.5 times specific heat sub 1 times 50 equals 1.0 times 4186 times 30. Which simplifies to 25 specific heat sub 1 equals 125,580. So specific heat sub 1 equals 125,580 divided by 25, which equals 5023.2 joules per kilogram per Kelvin. So, the specific heat of copper is approximately 5023.2 joules per kilogram per Kelvin. Let's recap what we've learned. Calorimetry is the science of measuring heat flow during thermal processes. It relies on the law of heat conservation. Heat lost by a hot body equals heat gained by a cold body. We also learned how calorimeters measure heat using constant pressure or constant volume methods. The water equivalent of a calorimeter is crucial to account for heat absorbed by the calorimeter itself. The key equation to remember is Q equals M sub 1 times S sub 1 times open bracket T sub 1 minus capital T close bracket plus the water equivalent of calorimeter times open bracket capital T minus T sub 2 close bracket. This process lets us determine specific heat capacity in experiments, providing critical data for understanding material properties. So, the next time you're cooking dinner or testing chemical reactions, remember that calorimetry is at the heart of understanding how heat moves and changes in our world. I hope this session warmed up your curiosity. Stay curious, stay cool, and I'll see you in the next class where we'll explore the hidden heat of phase changes, latent heat. Till then, keep your physics hot and your questions even hotter.